So today we're happy to have Jonas visiting us. So he's originally doing his PhD in Bochum, but this semester he's out visiting the University of Washington, working with Stefano Tessaro. So he's been working on looking at concrete security of signature schemes and authenticated chems, and today he's going to talk about some work looking at one of the NIST post-quantum signature algorithms.
Okay, thanks for the introduction, and thanks for the invitation as well. As Melissa said, I want to take a closer look at Falcon signature schemes, which is going to be standardized by NIST. Okay, like a short introduction. So our nowadays cryptography is mainly based on RSA or on D-log, and with Shor's algorithm together with like large-scale quantum computers, like most of our nowadays cryptography and standards are at risk. So the solution for this is post-quantum cryptography, and to standardize like this new type of cryptography, NIST has launched a competition already like 8 years back, and this competition has been going on for multiple years. And 2 years ago, in 2022, like NIST selected 4 algorithms after 3 rounds of standardization, and one of them is a key encapsulation mechanism, and they also chose 3 signature schemes. And the key encapsulation mechanism is Kyber, and from the 3 signature schemes, as the title could have given a hint on, I want to focus on Falcon. The other signature schemes are dilithium and Sphinx Plus, where Sphinx Plus is a hash-based signature schemes, and all the other primitives are based on lattices. Okay, so what are the advantages and disadvantages of Falcon? So first of all, considering all the signature schemes, Falcon is very compact. So compactness in terms of the size is a very crucial property of post-quantum schemes, because it's usually the bottleneck. So Falcon tries to achieve a very small signature plus public key size. And if we compare that to the other signature schemes that were selected, so here you can see the sizes of Falcon regarding the signature and the public key. If you, for example, compare it to dilithium, it gets like signatures that are like around a factor of 4 smaller. And for Sphinx Plus, it looks like even larger, the difference. And even together with the public keys, we can achieve like very compact signatures. Okay, so why not taking Falcon? So
Is there no level 3 option for Falcon?
No, there's not. So Falcon comes only with 2 parameter sets, one like with the ring of dimension 512 and one of 1024. And because like the ring dimension has to be a power of 2 to have nice properties, they don't get like a level in between. Right. Okay. So why not just taking Falcon if size matters? Like a lot of implementations are using dilithium right now, and one of the reasons is, which is a disadvantage of Falcon, is it's really complicated to implement. And this is mostly due to Gaussian sampling. So Gaussian sampling is one crucial primitive we will also take a closer look into later. So it's hard to implement Gaussian sampling, which is basically like sampling from a discrete Gaussian distribution. And to make this also like platform independent and like a standard is considered to be hard compared to, for example, dilithium. And I think, but I'm also not an expert in this. This is why like a lot of like actors in like industry, but I think you're like more experts on that, are a bit skeptical about implementing like Falcon compared to other schemes, or using Falcon. Yeah.
Question. So, how important is it that it's this Gaussian? Like, why not do some binomial?
So for binomial sampling, I don't get like, so I need like a property of the Gaussian sampling that I'm like have like enough noise, and I also have like noise that's flooding enough. So basically, if you imagine like a lattice has like a discrete structure, and I need like enough blur to get like a uniform structure in the lattice. So a binomial distribution is like not enough in that case.
So what does the lithium use?
The lithium, not entirely sure, but I think for the rejection sampling they use a binomial. But like, so this is so like the main difference here is that dilithium is based on the Fiat-Shamir paradigm, and Falcon is based on a full domain hash. And so like some structural differences. Why like in the case I have to like distinguish some or like make some distributions close enough to other distributions, and they are different in the Fiat-Shamir paradigm. So I have there more flexibility in the distributions from which I sample from. Right. So this is more a practical aspect. But another question, what about its security? So do we have provable security for Falcon? And if so, like what concrete security? And this is also actually a question, and on this part I will like focus on the remainder of the talk. Okay, so how does Falcon look like? So Falcon is following the GPV framework introduced by Gentry, Peikert, Vaikuntanathan. And GPV is proving like proposing a lattice-based construction following this full domain hash paradigm. And Falcon is also following this structure. So for example, also most of the people I talked to about the security of Falcon, they told me, okay, but I mean, we have GPV. GPV is proven to be secure. So where's the problem with Falcon? So Falcon uses a similar structure, so it should be fine. But actually, it is not. So if you look at the proof of a GPV, and you want to use just the same arguments to prove the actual construction of Falcon, it turns out that this proof is not sufficient. And one of the reasons is that, okay, this is like a small reason, but Falcon is defined over NTRU lattices, which you can think about as like just a special structure of lattices and not about like unstructured plane lattices. This is a minor point. I mean, we have like most of the tools we have for plane lattices, we can also adapt to NTRU lattices. But a bigger problem is that GPV is based on statistical distance for their proof. And if you use the same arguments for the statistical distance and you apply it to the Falcon parameters, then it turns out that distributions that should be close in the GPV proof are actually not close if you instantiate it with the Falcon parameters. So the proof doesn't go through or gives no security or not sufficient security. Yeah, and the third problem is that Falcon tries to avoids a correctness error. So if like I get a signature in the signing process which would not verify, then I repeat the signing process. And this is a difference in the construction which we also have to take care of if we analyze it, and GPV does not consider that. Like just has like a correctness error which can also be like if considering it asymptotically can just be avoided. But Falcon chooses this design, I would say. Okay, and so if we adapt these things, the question is, can we adapt it? So can we prove Falcon like from a provable security perspective? And if we can this, I can do that. What like concrete bit security can we get from Falcon? And this is also quite interesting because I mean like all the other schemes I showed you were like standardized in August. I think the standard like was published in August. Falcon is not standardized yet, I think, which is mainly due to the subtleties of the concrete implementation. But yeah, I think people were not considering security enough, but this is a personal opinion. Okay, so then what are our results? So first of all, we adapt some of the results from GPV, so-called uniformity results, to the Renyi divergence, which I will explain in a few minutes. So this is like a different a way of measuring closeness of distributions, which already has been used in cryptography. Then we give a proof of a modified generalization of Falcon. So what does that mean? First of all, we propose a very minor modification to actually prove Falcon. Without the modification, we are not able to. So the question is, like, can this modification still be applied that late in the process, since the standard has not been out yet, but we think it could. And it also comes with like a very negligible efficiency overhead. But I will also go into detail in a few slides. And the other modification we propose is to hash the public key. This is also like very common practice from an engineering point of view, that you hash the public key, or like good cryptographic engineering. But the current Falcon specification is not doing that. It also has been shown that we can get some other security guarantees if we hash the public key, and we found out that we can give a new one. So especially we can give tighter multi-user security if we also hash the public key. So the proof go through very tight, so we can increase the security there as well. Okay, and what do we mean by generalization? The proof we're giving, or the theorems, are parameterized by the trapdoor generation. So the trapdoor generation, you can imagine, is like part of the key generation. So in the key generation, I generate a trapdoor from my lattice, and the pre-image sampler, which samples from like a Gaussian distribution. And these components we are using like black box, so that they can also be replaced. And this can be like maybe interesting for the future, because, for example, as I said, the Gaussian sampling can be a bit hard to implement. And for example, there have also been like proposed other key generation algorithms, for example, for this trapdoor generation, so they could be replaced in the future, as well as the pre-image sampler. Okay, so the last point is that we optimize the security bound we get to get a concrete bit security for one sampler. And our results are the following. So we have like two Falcon parameter sets, a Falcon-512 and Falcon-1024. And together with our small modification, we get for Falcon-512, we get 100 bits of security for the full 2 to the 64 signing queries, suggested by NIST. But if we reduce the signing queries by a bit, then we can get 118 bits of security, provable security, for unforgeability. And for Falcon-1024, which targets NIST level 5, we can achieve 256. For strong unforgeability, on the other hand, things look a bit worse. I think targeting NIST level 1 is here a bit off. I think strong unforgeability we cannot talk about. Like for Falcon-1024, we could not achieve any security at all. But here I also have to mention, so these are like the provable security would give, so we don't give any concrete attacks. And we also don't claim that there could be like a better proofs. I will also talk shortly about this later, so this is just what we could prove.
So it's just that the reduction is so loose that it's weakness.
Here?
Yeah.
I think here it's a bigger problem. I think here it's the actual cis advantage in the end does not give more than 93 bits of security, for example. So I think here it's not a problem of the reduction, because maybe you could also come up with a better proof to get like a better bound for cis, but it's rather a problem of the concrete parameters than of the reduction in this case, I think.
Sure. So then what is the... I'm not confused. So what is the hard problem that it relies on that?
The security here? Or
yeah.
the security here is reduced to a cis. So,
But you think that the parameters are meaningless? In the sense they're like not good. So then in practice it doesn't rely on that, right? It relies on just its own construction as like the hard problem.
Sure. I mean, you could also define like the scheme is like, or like the assumption is the scheme is secure. True, but that is right. I think then, but then you cannot like give any specific claim, right? Like,
But isn't that what it is here, right? That's what you're saying. That's how it is. Or no, this is for the like modification, right?
Yeah, but I mean, for the I think the modification only makes it more secure, not less secure. Yeah, sure. I mean, if it can also say, but I think that's also a general question: how much do we want to rely on like provable security, or on like attacks that have been there or not have been there? But yeah, our goal was to reduce it to like some standard assumptions like cis or icis. No. Because I think we have like more trust in them than in like a specific construction. Okay, then I want to give some background and also like show you the concrete Falcon scheme. Yeah, the remainder of the talk won't have like much details on like a mathematical level, but on a provable security level. So I will go into some details of the proof, and because I think it's the main contribution. Okay, so first of all, I already mentioned it, the Renyi divergence. So for the Renyi divergence, I just want to give like a very brief overview. So it describes the closeness of two distributions and can be seen as a generalization of Kullback-Leibler, and has been used already like several years to get better security bounds compared to arguments with the statistical distance. So same thing we're also applying. And if you get like better security bounds, then you can also set your parameters better. And the Renyi divergence, I don't want to define it here, but what is important is that if you have like a Renyi divergence between two distributions P and Q, then it, like as we define it, looks like something like 1 plus a delta. So if two distributions are very close, then the value should be close to 1. They are far apart, then the delta grows. That also means that if we apply this in a proof, then we have to apply it multiplicatively. So this, like compared to the statistical distance, we would apply additively. If we have the Renyi divergence like this, we have to apply it multiplicatively. But this also means if you apply or if you query such two distributions that are close several times, like Q times in a proof, then you also get a loss of R to the Q. So this grows exponentially, and this makes also the loss very sensitive to the number of queries you're querying the distribution. Okay. That's just like some facts that I will use later. I will also remind you on these. Okay, so how is Falcon defined? So Falcon is defined like as for GPV is defined based on a pre-image sampleable function, which is here like function f, and we're computing this over a ring. Like for the instantiation, this will be a polynomial ring, but you can also just think about this like just having like addition and multiplication. And such a pre-image sampleable function is defined with respect to an h, and maps two elements to an element in RQ for a sufficiently large prime Q. So this is a forward evaluation of the pre-image sampleable function, and it's like this is the addition of the pre-image sampleable part. You can invert it to some extent. So there's also a function presam, which has a secret key. And the secret key you can think about like a secret key with respect to an h. So this will be the trapdoor in our instantiation. And with the trapdoor, you can get a pre-image for some element c in the image of the function. So what does that mean? You can get like an S1 and S2 that follow this function, so are actually a pre-image to C. But it would be easy to get just a pre-image. This pre-image should also be like following a certain distribution. And by D, I denote like a discrete Gaussian distribution. So this S1 and S2 should be actually distributed like a two-dimensional Gaussian distribution conditioned on being a pre-image. So conditioned on fulfilling this equation of the function.
And the H here is the NTRU public key.
Exactly. The H will be the NTRU public key, and the secret key is the trapdoor for the public key. Exactly. Okay, and Falcon is then defined like this. So in the key generation, I get such an H, as you said, like as a NTRU public key and a trapdoor. But more important, what's happening in the signing procedure. So this is just like a very condensed version of Falcon. So Falcon's much more complicated, also doing like, I don't know, like FFT operations for efficiency. This is just like the condensed part which we want to prove, like the core which gives the security.
And you already put the public key in the hash.
Exactly, this is also like a difference, exactly. So first of all, I sample a salt, so it's a probabilistic signing procedure, and then I hash my salt together with a message, and as you said, here we already applied the modification that we also hash the public key. Right. And then the crucial procedure is this pre-image sampleable function. So then if I hashed my message and my salt to a challenge, I get a pre-image from this challenge. This is only possible, or should only be possible, with the secret key. So then I get an S1, S2 that fulfill the function equation. And I do this until my pre-image is small enough. So it should follow a Gaussian distribution, so it should be small, like in the sense of like the norm of it should be small. But yeah, since I'm sampling like something which is close to a Gaussian, it can also land in the tails. So the probability should be low, but can happen. So I repeat this until I get a sufficiently small pre-image. This is like to ignore the correct, or to get rid of the correctness error. And then I output the signature. I just need to output one of the elements in the salt, because the verifier in the end can compute the other element and then has to check for smallness or shortness. Yeah?
Is the small requirement, is that to make it efficient, or is that like a security thing that part of the kinds of using?
So here it is to ignore the correctness error, but overall to verify it here is a security guarantee. So if I wouldn't have that, so just check for pre-images, then everybody could compute this. Like large pre-images is easy to compute.
So what is the correctness error?
So here is none. A correctness error would be if I correctly, or if I use this pre-image sampling, but I get pre-images which is actually large. Even so I use this functionality, since it should be close to a Gaussian, it can also land in the tails. And so I created a signature honestly, but it still doesn't verify, because the verifier says, oh no, it's too large, I don't accept it. So if I choose like parameters such that my tails are very unlikely to be like hit, then there's no correctness error, but as we see, there would be a correctness error. This is ignored by that. Okay, so this is how the current Falcon specification works, and what we propose is the following change. So here we sample the salt outside of this loop, and we propose to do it within the loop. So if we fail to get a sufficiently small signature, we say that it is better to start with sampling a new salt, getting a new challenge for the hash, and then resample. Of course, this part is a bit less efficient, because I also have to choose my new salt, have to hash, and so on. But the thing here is that the pre-image sampling is basically the bottleneck of the whole construction. So like efficiency-wise, it takes much longer than computing the hash and also some other operations. So the hash is also computed, or from the hash is also computed the FFT representation and so on. But these are way smaller than the pre-image sampling. Also, since it's following a Gaussian distribution, it's not very likely that this happens. So in expectation, it's like between like a bit larger than 1 time I have to like execute this procedure. So the expected value is 1 point something. Okay. So then we'll see why this modification is necessary, or maybe it's not necessary, at least for us it was necessary to prove Falcon to be secure. So first of all, I want to just give a short overview how GPV worked, or how the proof worked, in also a very condensed version. So what is GPV doing? GPV is doing a reduction in the end to cis. And the cis game means I get like a challenge H, and I have to output a short solution, so short in the sense of the norm being bounded at most B, has to be a non-trivial solution which maps to 0. So basically being a pre-image with respect to this function of 0. Yeah, so you can also like this function is like basically all the values that map here to 0, but construct a lattice. But like if you just use this ring notation, it's like a bit easier to depict, but they are equivalent. Okay, and the reduction has like several steps. I just want to show you the 2 most important steps. So we use an unforgeability adversary to build the reduction in the random oracle model. So the adversary has access to random oracle and to a signing oracle. And in the end, has to output a forgery. And the first step to prove that is to program the random oracle by choosing some values S1 and S2 that follow like the distribution on the domain, and compute this function forward. So if I do that, then I output the value of my function, but I have a pre-image like programmed for this value. For this to like be sound, the output of this function needs to be like close to uniform, otherwise the proof won't work. Okay, so if I program the random oracle, then in the next step I can simulate my signing oracle by just choosing the pre-images I sampled during programming the random oracle. Right, so this S1 and S2, they're sampled here are pre-images for my output C, and here I have to find a pre-image for the C, so I can just take the one. Okay, and then in the end, I can make the reduction. So take the challenge H and forward it to the adversary and find a collision. A collision I can find like a collision for for the same challenge C by taking the forgery, which should be correct, so it should be like a pre-images for the challenge C. And I take the other pre-images which I programmed in the random oracle. And if I find a collision in the function, I can just subtract the pre-images and I have a pre-image to 0, which is exactly my cis solution. Okay, then we want to take a look at the actual Falcon proof. So where does this proof fail? So we have a similar structure. Now we're reducing to entrances and not to cis anymore in the end. So our H is not necessarily uniformly distributed, but distributed as entry keys are distributed. But there's no known attack that it should be easier. To win the entry cis game than the cis game. But yeah. Okay, so same procedure again. Adversary gets a public key, gets access to random oracle. This is just now uniformly sampled from RQ. That was the domain of our the codomain of our function, and gets access to the signing oracle. Signing oracle also proceeds just normally for this challenge public key H. Okay, so the first step would be to program our random oracle again. So in this specific case, choosing some S1 and S2 following a discrete Gaussian distribution and computing the output for the function, which was exactly this equation. And then we store S1, S2, and our C. Okay. So let's take a look at this. So this was the random oracle we programmed. So the question, if like the reduction should go through, is this distribution actually close to uniform? And the question here is, what does Gauss mean? I also already hinted it a few slides ago, and the question for statistical distance is no. To make more specific, for the concrete parameters, the statistical distance would be only 2 to the minus 35. So this is not sufficient for making it like a security argument. Right? Okay. So yeah, this distribution. And if you use the Renyi divergence, then we can do it. So the answer is yes, or maybe. I will explain maybe. And we proved the following corollary. That might be a bit overwhelming, but I'll just tell you two things to look at. So this is an adaptation of the GPV, or one of the GPV lemmata. And the important part, so what do we need? We need the standard deviation to be sufficiently large. And specifically, so here we have the NTRU lattice, and it has to be at least as large as the smoothing parameter. And the smoothing parameter gives us nice properties of the lattice, or especially of Gaussians. And one of these properties is such a uniformity property.
What is the S there?
The S here is this standard deviation of the Gaussian, so here. Right, and if we have this, so if we have these like nice lattice properties, then we can show that the distribution of P and the distribution of Q, which is exactly the distribution we programmed here, are Renyi close. And Renyi close in that sense, so we have 1 plus a hopefully small term, and this term depends on A, which is the order of the Renyi divergence, which I ignored so far, but this we can set more or less arbitrarily. So this can be small, and also on epsilon. And the epsilon is the error of the smoothing parameter. So what does that mean, or what is the intuition behind that? So if I want like a more secure scheme, then I have to set a smaller epsilon. But a smaller epsilon comes with a larger smoothing parameter, so the smoothing parameter grows, so I also have to set a larger standard deviation. And a larger standard deviation leads to less efficiency because I get larger signatures. So this is the trade-off here. And yeah, so like in a normal approach by constructing a scheme, we would set our parameters such that we get like a secure scheme. Here we had to do it like the other way around because the parameters were already set, but we need to prove to fulfill these parameters. Okay, so why did I say maybe? So it turns out this is sufficiently small, this term, for the actual Falcon parameters, but we've also seen that the Renyi divergence depends on how often I want to query a certain distribution. So we cannot say, like in general, that this is sufficiently small. It depends on how often we query the distribution. So how we have to take this to the power of q if we want to query the underlying distributions q times. So it depends.
So the reason for this statistical distance that is like non-negligible is the structure from the NTRU lattice. Is that what causing that?
No, you could also in the NTRU setting, you could also set parameters that you fulfill like a statistical distance to be close. That would also be possible. The reason is that Falcon wants to be more efficient and more compact and sets the parameters that they don't claim or didn't plan to fulfill statistical distance, because in other places they already use the Renyi divergence. So this is not to use the Renyi divergence here. And they already set parameters that they don't fulfill the statistical distance, but only a Renyi divergence. Yeah.
When you're talking about the number of queries, is that like the number, that's actually the number of queries you put to the hash function is the number of like signatures you're generating or something?
Exactly, yeah. So so in the proof, I want to change these two distributions, so it depends on how often I have to change them. And this will be either like random oracle queries or signature queries.
So how should I think of this? Statistical distance is like non-negligible, Renyi divergence, maybe it's small. So what does that tell me? That is this secure or?
I mean, if you show it to be secure with the Renyi divergence, then it is fine. Yeah. I mean, it depends on the concrete bound in the end. So you lose, for example, something like 1 plus something small. So I don't know, if like the 1 plus something small leads to like a loss of 2 or 4, then you would lose 1 or 2 bits. So this will translate to like a concrete bit loss in the end. Yeah. Okay. So then we program the random oracle. That is fine, like depending on the queries that we'll see later. So the next step is to simulate the signing oracle. So for the signing oracle set, we just take the S1 and S2. We programmed in the random oracle, since we always like query the random oracle here. We should have such an S1, S2. Okay, so what do we need to make this step go through? So we need the pre-image sampler. So this function we used before should be close to a Gaussian distribution. Why? This S1 and S2 we chose from a Gaussian distribution by programming the random oracle. So these both distributions should be close as well. And there again, they're not statistically close, but Renyi close. And this was like based on this, Falcon set their parameters. So this they considered already, and this also has to be shown. It depends a bit on the sampler, but this was there already. But another question is the pre-image short enough? Right? Because if I get my pre-image, which is like with respect to a Gaussian distribution, it can still land in the tails. And my problem here is in the pre-image sampler is a probabilistic algorithm. So in the original scheme, it's not a problem if I have a pre-image that is too large, because I just can repeat and sample a new one. But here I can't do that because I just have one pre-image from my C, so I can just take that and I'm stuck in the simulation if I have to repeat. So it depends on like how probable it is, and that I'm landing in the tails, or that I'm like small enough, and the probability here that I'm landing in the tails, or here is it like differently, but landing in the tails is 2 to the minus 14, which is quite high. At least too high for making the security argument going through. So we need another solution. And one possible solution would be to program the random oracle not on a Gaussian distribution for the later pre-images, but on a conditional Gaussian, conditioned on being small. This would be a possible way, but the problem is that the corollary I showed before does not work there anymore. So the corollary could only show for like an unconditional Gaussian, and this is also a crucial point like in the proof of the corollary. So maybe this can be shown, but yeah, not with the tools we developed there. Yeah.
Wouldn't it seem like it shouldn't be possible to make the proof work that way, since you'd be like noticeably changing the distribution of the hash function?
Yeah. So I'm not like 100% sure, but this is what also would be my guess, that it should rather not be possible. Yeah, yeah. But I don't have like a proof to claim that actually. We didn't do that. Yeah. Okay. And the other solution is what I told you before. So changing the structure of the scheme. So what does it help? So if we also repeat by sampling a new salt, we can solve this problem because we get a new C here. So we also can program a new pre-images for a new challenge. So now we have the chance that eventually we get a pre-image that's small enough. Okay. So now we we simulate the signing oracle. So sign plus refers to the proposed modification for Falcon. And now we can simulate the signing oracle without knowing secret key. So we can apply our reduction. So get the challenge, age, and then compute a solution for entrances. And yeah.
The fact that you put the R in there, does that mean that you don't need to consider quite so many queries in your like programming your oracle, because you sort of only need to program it on the R's that you picked during signage? So presumably you potentially program the random oracle even for other
Yeah, okay, I got it. It's a good question. So, like in this proof, or in this like boundaries occurs here, I also needed to program it on all the other random oracle queries because of the reduction now. Because the reduction now works in like finding a collision again. So I have to take the forgery, but also one possible query to the random oracle. Because the forgery could be of like a random oracle query which was not queried to the signing oracle. So for strong unforgeability. So either I have to do a guessing argument, which we also do, or like hybrid argument for that, or I have to program all the random oracle queries because I don't know on which one the adversary will forge in the end.
So if you don't care about strong unforgeability, then
yeah, if you don't care about strong unforgeability, then you still need it. As we I will also show the bound then, but you still need to guess which query could be, which random oracle query could be used. Yeah, it's not, yeah. Okay, so, right, so we compute like our S1 star, S2 star from the forgery, subtracted and get such a solution. A solution that maps to 0, and we can also see that our bound is sufficiently small because we have 1 beta from the winning condition of the adversary and 1 beta from the smallness of the programmed value. So it's a 2 beta. Okay, so how does our security bound look then? So first, the bound from the theorem I depicted in the overview. So there are much more terms, but the most important terms is the disadvantage, and we have our Renyi losses here. So we have a Renyi loss from the uniformity result, programming the random oracle. This is applied QH times because I need to be able to find a collision for any of the values. And I have to this pre-image sampling Renyi divergence, which is only applied in the signing oracle. So this is QS times. Okay, so what does that mean for concrete like security? So the problem here again is that the Renyi arguments rely on the epsilon. So the epsilon concretely for Falcon is set to this value, which is with respect to the signing queries and the security parameter. This is a very common choice, and this is like choose like that to support QS queries and the security parameter of lambda. So if I apply such an epsilon, get like my Renyi results, and apply this Q to the S times, then I lose around a bit of security or something small. So for QS this works, but this means that it will fail for the first term. For the first term I have QH, which is like quite larger, like for NIST 2 to the 96, so this term completely explodes. So if we use this strategy, we cannot show any security. That's why we also change our, so this was the bound from before, that we also prove something else. And this is reducing this term to QS. So only program the random oracle, I think in the direction you mentioned, only for the QS values for the signing oracle, but then I still have to guess one additional query on which I can do like my reduction in the end for the collision proof. So that's why I get like a tightness loss of QH here. Right, so this bound has like a tightness loss of QH, and it also has another disadvantage, as you've seen before. So the cis bound here is still too large. So we have a bound of 2 beta. And if we plug this in, like we use a lattice estimator for that, so what would be like the concrete bit security for this term, for the concrete parameters and for Falcon-512, that's only 95 bits of security. And for Falcon-1024, that's no security at all because the bound is even larger than the modulus that's used. So this can be broken trivially. Okay, so we also have another bound, and this bound is only for unforgeability. So what we do here, so we still have these loss as before, but we can reduce the bound to only 1 beta, which is also, I think, a a common technique to, yeah, basically, I mean, it's also reduced to ICEs, but like to not be able to reduce to any queries that are like strong forgeries, like answering queries for which I also, do reductions for challenges that already also has been queried to the signing oracle. Okay, so then let's stick with this bound, and there's one thing I ignored so far. So in the beginning I told you that if we reduce the signing queries, then we get better security. And the question is, why is this? So also in the bound before, I ignored one parameter, and this is due to the repetitions. So I don't only have QS signing queries because of the loop. I have like some upper bound constant times the signing queries, which is, I think, also inherent from the construction. So this number is not very large. So concretely for Falcon, it's like 5 or 9, depending on why is it 5 or 9, or 5 or 9 to get like good security. So make it like sufficiently, the loss sufficiently small. So 5 or 9 might not sound very large, but as we've learned, like the Renyi arguments are very sensitive. So even if I increase this by a factor of 5 or 9, yeah, this reduces security. Yeah.
Why is it the maximum that's important versus like some, I don't know, expected upper bound, or some over all the queries?
Mm-hmm. Yeah. So this we could also do. So we could also just compute the sum of all of them. The reason is that it led to approximately the same like security in the end. And that's why we chose to, because it was easier to just choose an upper bound, because it was a bit cleaner in the proof. But
it seems like it should say, like, because you said usually expected it's like 1.
Yeah, 1.
Yeah.
That is true, but I mean, I still need all of the queries to fulfill like that they have to. Okay, yeah, you are right. I'm not sure. I have to check again. But when we computed it, it was like it led to approximate. I mean, it were like less. Like the overall was like way less values, true, but it led to somehow the same loss. I'm not sure. Well, yeah, maybe I have to check that again. That's a good point. Right. Okay, so what we're doing to compensate this loss is just to decrease the signing queries to achieve at least a better security. And I mean, this is a trade-off. Like, I think people should decide in the end what makes sense. But at this, how we can compensate this. And, yeah. Okay. So what about the final bit security? So, like as an example, for target NIST level 1 and Falcon-512, we would analyze the bound as follows. So we get like an ICEs advantage of 120 bits. And for maximum number of signing queries 2 to the 64, we also now have another leverage. So the Renyi order we can also set, and we can also optimize this Renyi order. This depends a bit on the bound. So if you look at the bound holds for every Renyi order, and you can just, so this is not about like the parameters or something like this, just to get tighter bounds. But if the QS is 2 to the 64, then we get such a Renyi order and lose 10 bits per application. And we have to apply it for pre-image sampling and uniformity. And if we allow only for 2 to the 57, why 57? 57 was the largest value, which gives only 1 bit of loss per application. So here we get like, yeah, basically like the tightest security, but with less queries. And that's how we come to 118 bits of security. One remark is that this table ignores the QH loss we had, like the tightness loss, but which is also happening, I think, in practical applications a lot, because it's like a proof artifact, and people for practical parameter sets usually ignore that. I mean, from a provable point of view, it's like not a good idea to ignore it, but I think that's what, for efficiency reasons, happens a lot. And if we would apply it like this, we cannot achieve any security. We would lose like 96 bits again. Right, but there are some improvements.
Where did the QH come from again?
And the QH comes from the application of a hybrid argument. So I don't know which query of the random oracles the adversary will use to output a forgery in the end. Yeah. Right. Okay, and just to for completion, just as I said in the beginning, is like we get 256 for normal unforgeability, plain unforgeability for Falcon-1024. Okay, then also close to the end, 3 minutes. Some future directions might be interesting. One thing is that the bit security I showed you on the last slide is computed with respect to the client sampler. So this is like, you have to be a bit careful. So the client sampler is not what is actually currently used in Falcon. So this does not adapt to the concrete Falcon specification. For the FFO sampler, there's no analysis yet. So this would be like an open thing. Like it should be expected to be in the same range, but don't have proof for that. So this would be a thing to analyze the FFO sampler. That's a sampler that's actually used in Falcon, and plug it into our proof. So our proofs are generic so that they work the same, but I have to compute the bound in the end again, so the bit security. Then one could improve like the proof techniques. For example, the QH loss. For the QH loss, this is not in the work right now, but we have an idea how to remove the QH loss as well to get like a tighter bound, or remove it move it to the assumption to make the claim a bit stronger, to actually ignore the QH loss. And another open question I think is a QROM proof. Currently we only prove things in the classical ROM, and most of the things also live to the QROM. For the Renyi diversion, it's not so clear. So as I'm not an expert on the QROM, but as far as I know or talk to people, there are no arguments to lift Renyi arguments also to the QROM, like when I program something in the ROM or QROM, which is only Renyi close, not statistically close. I think this would be also an interesting step to go. Right. Okay, to summarize, contributions are like our first modification, first formal proof of the modified version of Falcon. For that we adapt some of the results from GPV to work with the Renyi divergence, and optimize then the security bound to get a concrete bit security for the client sampler, not the FFO sampler. So be a bit careful about that. And right, so if you want to have more information, like in the paper and ePrint, or we can also talk about it if you're here. Yeah. Thank you. And if you have any questions now, also, I mean, I don't know how the time schedule is, but I'm happy to.
We have a couple.
Yeah.
So how is the Falcon team thinking about the modification?
Yeah, so we only talked with some of them, but they were quite open to it, because they say it's not a big modification in the sense that just like moving the sort in there. We also open a discussion on the PQC forum, so other interested people might also be at there. But so from one of the authors there, and also one of the authors we talked before about the results, they were quite open to it. But they also said, but probably you're also more experts on, I think they don't have a lot of saying anymore, because I think NIST has to decide what is happening at this point.
Has NIST said anything yet?
No, not that I know. No. But I think it makes sense. So I mean, maybe it can also be proven to be secure like this, but I think it's just
In most cases, it doesn't change.
Yeah, exactly, and it just makes it potentially more secure.
Any other questions? Anybody online? Thank you very much.
Thank you.